Okay. Now we'll look at the standard graphics pipeline. So as far as this course is concerned, we'll be looking at graphics into two sections. One is the modeler part, where we've already modeled objects in the scene in the 3D world, and an interface file is actually transferred to the renderer. So render basically takes in, information from the modeler and takes geometry from the modeler. It sends it through the graphics pipeline and finally creates the image. So for the scope of this course, we assume that we already have modeled, or somebody has modeled the objects and kept it in a repository, and those files are actually transferred to the render. So once the render gets this interface file, it sends it to the graphics pipeline, and the graphics pipeline, in a broader sense, it forms of these blocks. We have a transformation block, there's a clipping block, and there's a rasterization part. So initially it gets these vertices. Vertices are basically the vertices in the sense like vertices of polygons. Mostly we deal with vertices of triangles or quads. So these vertices has to undergo some transformation, mostly in terms of transforming it from one coordinate system to another. So once it's there, those transformations are done. Also, projection is a part of this transformation. We need to do some clipping. Clipping is because not all vertices or not all objects are to be seen by a particular camera angle. So there's in a particular field of view, only a portion of or some of the vertices or some of the primitives will be shown. So the other ones which are actually falling out of the field of view, they have to be clipped. And finally, to display it on a particular uh, viewport, we have to do a rasterization and convert them to pixel, because here we have some shapes, and those shapes has to be pixelized, fragmented, and they have to convert it to pixel to be shown on the viewport. So these are the broad way of describing the graphics pipeline. Let's before going further, let's revisit the image formation model, because we've already seen graphics hardware or software try to mimic the synthetic camera model, and we have an API in which we can actually specify the objects, materials, viewers, and the lights. Okay, so one way of actually getting obtaining these images is to mimic the physical approach. So some of the commonly used approach which mimics this image formation from the model is known as ray tracing. So in ray tracing, what happens is follows a rays of light from the uh, objects from the source to the eye. So, but normally there are multiple. When we start from source to an eye, there could be multiple. Light rays which may not end up at the viewer. So it's normally a practice to go from eye to the objects. So the advantage is that it can handle multiple global lighting effects, like multiple reflections. So a light from a light source can go to an object, hit that object, again get reflected and hit another object. There could be multiple reflections. There could be other phenomenon related to light, like translucency, or all those things is taken care naturally. But one of the major drawbacks is it's very slow. We have to take care of lots of light rays, keep track of all the light rays. And one of the most fundamental drawbacks is it requires the entire data to be available all the time, because we need to know how it interacts with every object in the particular scene. So at any point in time, all the light sources and the objects in a particular scene has to be available in the memory. So that is one major drawback. And there are also other approaches like energy-based approaches called radiosity, but these approaches are also very slow. But generally, it's a common practice to use local lighting approach. So here there are some disadvantages with the local lighting approach in the sense it cannot compute color or shade of each object independently, because when you try to do this independently, what happens is there could be effects like shadow effects where objects block light. There could be also light which can be different reflected from object to object. So if you are actually considering only one object at a time, uh, all these effects may get neglected. But there are some ways in which we can actually try to model this in an effective way without compromising a lot on the photorealistic quality of the image. So the local lighting approach is mostly commonly used in graphics pipelines. So why not ray tracing? Because ray tracing, even though it's more physically accurate, uh, it is it is it's possible for simpler objects and simpler point sources, but it's slow and not well suited for interactive objects. So we go for the more practical local lighting approach. So this is the practical local lighting approach, which graphics pipeline uses. So this is a more detailed look at what we have seen earlier. Earlier we've seen vertices that they go into something known as, so let me look at this. Yes, there's this transformation block. More detailed version of the transformation block is vertices, they have this vertex processing. Vertex processing, we'll look into details of all these things in the coming slides. There's vertex processing, there's vertex assembly, and it's followed by clipping, rasterization, and fragment processing, and finally we end up at the pixel level. Let's look at vertex processing. This is the first block. What happens is we have vertices. Vertices, mostly they are concerned, vertex processing is concerned with converting vertices from one representation to another coordinate representation. So objects will be initially in the object coordinate system. So we have to transform them to a camera coordinate system and then to screen coordinates. So basically these two are in object coordinates and camera coordinates are in 3D. Then we have to take them to the screen coordinates, which is in 2D. So it involves some sort of transformation and projection. So all these transformations are represented in terms of matrix multiplications. After a vertex processor also computes the vertex colors and sometimes the vertex normals as well. Okay. Yeah. The next step is, okay, let's also look at projection in a bit more detail. So in vertex processing, I've already mentioned that there are coordinate transformations and projection. So in projection, we are going from view volume to the image plane. There are two major types of projections. One is the perspective projection, which is similar to the synthetic camera model, which we have seen. We have projectors, projecting lines, which actually converges at the center of projection. This is known as a perspective projection, the way in which we actually see things in the real world. There's also something known as parallel projection, where the projection lines are not converging to a particular point, but they are parallel. But it's not a practice to use different projection pipelines in graphics, because it's more convenient if you have a unified transformation pipeline. So what we do is we can view one as a specific case of the other. So one way of viewing it is parallel projection can be viewed as a specific case of projection, a perspective projection, where the center of projection is actually located at infinity. So that is one way of looking at it. After vertex processing, which involves the coordinate transformations and projection, we have the primitive assembly. The primitive assembly, basically what it does is we have the vertices, but we have to assemble the vertices into some sort of primitive, some basic geometric shapes like line segments, polygons, curves, or surfaces. Some of them only supports line segments or simple polygons like triangles and quads. We have not that all these primitive assemblies currently. We're discussing 2D primitives. We're not considering any 3D primitives. In the clipping phase, which is the next step of the pipeline, the objects outside the view volume has to be clipped off because we are looking at a particular view, viewing field of view. So this we have a center of projection. We have the viewing plane. Only the objects which are in the viewing frustum, which is like a clipped version, like if you have a pyramidal shape and if you cut top portion of it, you'll get a frustum. And only the objects which are actually part of the viewing frustum will be visible on the view plane. So we have to clip out all the objects which are outside the viewing frustum. Also, the next step is rasterization. So once we have some primitives and parts of it, and some primitives got clipped, or parts of it got clipped, and now we are left with some fragments. We are left with some primitives which are actually part of the viewing frustum. But now we have to convert these shapes, these primitives, into pixels. So rasterization, what it does is it basically breaks down a shape into fragments. These fragments are not essentially pixels. They are actually potential pixels. They have not yet got converted into pixel, but just a phase prior to that. And these fragments are actually have a location in the frame buffer. So in the sense, a frame buffer is a 2D array, and we all know that what are the corresponding coordinates of each fragment in that corresponding frame buffer. Also, it has some color and depth information. The vertex, how do you get these attributes? It's actually interpolated mostly by linear interpolation from the vertices. So the fragments has to be, this is what is done in the rasterization part. And the next step is what is known as fragment processing. So fragments are processed to determine the color of the corresponding pixel in the frame buffer. Mostly what is being done here is multiple objects can give you fragments, but the final pixel which you're going to see could be from mostly from one object. So there's something known as hidden surface removal which has to be done. We have to do some sort of sorting and see which is actually occluding which surface is actually hidden from the imaging plane, and we have to do the hidden surface removal. And finally, after fragment processing, we get the pixels. Okay, this is what is the standard graphics pipeline.